Let us talk about the force law for SHM and expression for the time period. Now, when a body is in equilibrium, that means the forces on the body add up to zero. Now, if that body that is in equilibrium is given some displacement, three possibilities arise. One is, if the body is given a small amount of displacement and the body comes to rest after traveling some displacement or traversing some displacement, the body is said to be in neutral equilibrium. If the body continues to move in the direction of force, the body is said to be in unstable equilibrium. If the body, after being disturbed, comes back to its original position, that body is said to be in stable equilibrium. Talking of the simple harmonic motion, when a body is disturbed from its mean position, it comes back to the mean position after traveling to extreme position. So, as the body returns to its original mean position, the SHM takes place under the condition of stable equilibrium. That means there is a force that is opposing the displacement and restoring its original position or the mean position. We see that if the displacement of the simple harmonic motion is equal to y, that is equal to a sine of omega t, the acceleration is equal to minus a omega square sine of omega t. As here a sine omega t is equal to y, we can say that a is equal to minus omega square y. So a is the acceleration that is always directed towards the mean position. So the restoring force F is equal to mass into acceleration, and that is equal to minus m omega square y. Under the action of the restoring force, the body is brought back to its mean position. So this is the value of the restoring force. F is equal to ma, that is equal to minus m omega square y. The restoring force can also be written as F is equal to minus ky, where k is equal to m omega square. This k is called as restoring factor. Now this f and this f is the same, so we can equate these two equations. By equating these two equations, we get the value k is equal to m omega square, or omega square is equal to k divided by m. Now this k is spring factor and m is inertia factor. So omega is equal to root of k divided by m. We know that omega is the angular velocity, that is 2 pi divided by t is equal to root of k divided by m. Solving for the time period equals to 2 pi root of m divided by k. Or we can say that t is equal to 2 pi root of m is the inertia factor, and k is the spring factor. So for calculating the time period of all the simple harmonic oscillators or simple harmonic vibrators, we have to watch out what is the inertia factor, and we have to watch out for the spring factor. Discussing further, so if t is equal to 2 pi root of m divided by k, now this k is a restoring factor, as f is equal to ky, taking the magnitude only, f is equal to ky, we can say that k is equal to f divided by y. Now putting the values here, so t is equal to 2 pi root of m divided by f. F is equal to mass into acceleration, so m into a divided by y. This m and m goes, that comes equal to 2 pi root of y goes up to the numerator, y divided by a. Now y is the displacement, a is the acceleration. So an alternate equation for the time period is 2 pi root of displacement divided by acceleration. This way we have got two equations for the time period. One is time period is 2 pi root of inertia factor by the spring factor, and here t is 2 pi root of displacement by acceleration. We can calculate the values, or we can calculate the frequency as 1 upon t. Here we can calculate the frequency as 1 upon t. Thank you.